Hey everybody, Dr. Retzik here. This is a continuation video of section 14.6, wherein we are learning about tangent planes to surfaces. Let's get started. Imagine you had a surface that was not so easily recognizable as z equals f of xy. What if you had something complicated like this? And it was sitting in 3D space, like this. And say you were interested in making the tangent plane to this surface at, say, this point right here. Well, you know what you need. The ingredients to make a plane are what they are. You have a point you're interested in. You need a normal vector. Once you have that normal vector, and you have the known point where you're building the plane, then it's a simple matter to build the plane. Now, for surfaces that are of the form z equals f of xy, we developed in our intro video for 14.6 the exact process by which we can write that tangent plane. But that was all assuming we could get z equals f of xy. When we can't get z equals f of xy, what we do is we treat the surface as the level surface for a function of 3 variables. So maybe what's on the left-hand side of that equal sign is very complicated, and it's something that you either don't relish trying to solve for z, or perhaps can't be solved for z. And so all you know is you have this big relationship between x, y, and z, but you can't get it explicitly z equals f of xy. Well, that's fine. Get everything with x, y's, and z's on one side. You can leave constants on the other side, and then name the left-hand side capital F. And what you know is, in thinking of that surface as the level surface for the function capital F, meaning that's all the points x, y, z in 3-dimensional space that make big F come out to C. Knowing that that's a level surface, you know that the normal vector you seek is nothing other than the gradient of big F, evaluated specifically at that point on the surface. So if that's the normal vector, and this is the point, say x naught, y naught, z naught, on your surface, then immediately, once you have your hands on the gradient of big F, again, you can write that tangent plane. So in this case, the tangent plane at the point x naught, y naught, z naught is simply gradient F dotted with x minus x naught, comma, y minus y naught, comma, z minus z naught. Comes out how? How does the blue vector sit relative to the orange tangent plane? It's perpendicular, so the dot product is 0. Now, typically people write that like this. In other words, the plane is df dx, specifically at x naught, y naught, z naught, times x minus x naught, plus df dy, specifically at x naught, y naught, z naught, times y minus known y, plus df dz, specifically at x naught, y naught, z naught, all times z minus known z, comes out to 0. And what's in this box here actually matches what was in the box developed in yesterday's video by chain rule. Do you remember back in the day when we computed dz dx as negative x partial of big F over z partial of big F? That relationship is what relates this box to the box developed yesterday. That one and the corresponding one for dz dy. So if you could solve and get z equal stuff with x's and y's, then this box and the previous box would match. But this one is more flexible because you aren't compelled to solve for z, which means even in situations where you might choose to solve for z, you certainly don't have to. Like, what if you had this example? What if you were interested in a sphere? Say, centered at the origin of radius 2. Certainly, you could solve that for z and build the tangent plane at any point according to yesterday's discussion. But I feel like that's more trouble than it's worth, because when you solve that for z, you take square roots, and then you have to decide, oh, am I on the upper hemisphere? Am I on the lower hemisphere? How do I know? Do I take the positive or the negative square root? Plus, the derivatives are just much more involved. There's chain rule. It's just annoying. But it's just so clean to just name this capital F of x, y, z, and just cut straight to that box. So this gives you an alternative to yesterday's discussion. But remember, the picture is identical. All you're trying to do is find a normal vector so that you can build your plane at the point in which you are interested. Great. Okay. The only other thing we want to do today is think about why a person would want to know the tangent plane to a surface. So I'm imagining this old Calc 1 drawing. In Calc 1, you had a picture like this, say. Good old XY coordinate system, the good old days. And say you had that function, y equals f of x, and you made the tangent line to that function, say, right here at this point. So let's say that's the point x naught. Now you can see that the orange tangent line, let's call it L, which is a function of x, and the actual function of x, that's the black curve, you see they agree right at the tangent point because that's how you built that tangent line. And though they don't agree at points near to that tangent point in this drawing, if you zoom way in, you would see something like this. There's the purple circle. There's the function. And here's the line. And what you can see in that depiction is that near that tangent point, there's really not much discrepancy between the actual curve and the simplified linear curve. As long as you don't wander too far from the point x naught, the z-values on the orange tangent line and the z-values on the black curve really aren't that different. And therefore, you can use that orange tangent line to approximate the values of your function near the point where you built the tangent line. This is called linear approximation, and this orange tangent line, this is sometimes called the linearization of f at x naught. Okay, so that's what the story was like in Calc 1. You say, I have a complicated function. I'm interested in knowing its values near some certain spot x naught. I will write the tangent line instead, and I will use that to estimate my function. Here in 14.6, we are doing the exact same thing, only the setting is not a curve, y equals f of x, but rather a surface, say z equals f of xy. It is happening not in two-dimensional space, but rather in 3D space, like so. You are interested in your surface at a certain point. The point of interest down in the domain is not simply x naught, but now x naught comma y naught. You are building not the tangent line at that point, but rather the tangent plane at that point, which we are adept at. And if we are interested in plugging points near the known point into the surface, well, we may as well plug them into the tangent plane and say, you know what? It's not exact, but if this function is differentiable and we don't stray very far from the point x naught, y naught, then the difference in output values, the difference in z values, the difference in height, altitude above the xy plane, there's not much disparity between using the surface itself and using the tangent plane. And just like in the Calc 1 setting, this thing has a name. This is called the linearization. It's a linear object, it's a plane, and it is itself a function of x and y. And the upshot of the entire discussion is this. F of xy is pretty reasonably approximated by the linearization for points xy reasonably near the known point x0, y0. And since you guys are good at building tangent planes, you can go ahead and build that tangent plane at any point you like, and you can use it to approximate the values of your function near that point. So that's part of the purpose of coming to grips with the idea of tangent planes. We will see that partial derivatives and tangent planes will also play a role in section 14.7 at the beginning of next week, where we start to think about the several variable analogs of good old max-min problems. But as far as 14.6 goes, that's the idea. We can build tangent planes, use them to approximate surfaces. All right, I think you got enough to go on. Try those suggested problems and come to class with questions or comments. All right, see you next time. Bye.